Okay. Thank you for listening my presentation. I'm Taiga Ezura from RICOH company. My presentation title is Technology Development of MEMS Process by Utilizing Multiple Creative Technologies. So this is my presentation outline. First, I talk about the introduction of my research, MEMS, and our approach, Fukuhara method QFD. Second, I explain about the target system in this research. Third, talk about the experiment, result, and discussion. At last, conclusion. Okay. Then I talk about the introduction. So starting with my presentation, I would like to explain what is MEMS. So MEMS is short for micro electromechanical system. So this is technology for micro-scale devices. So for example, look at this figure. So this is our micro mirror array device fabricated in our company. So in this device, these rectangles object are mirrors, and each one moves independently. So the mirror size is about 10 micrometers. So it's smaller than the thickness of the human hair. Generally, the MEMS devices are fabricated by 3 steps. So deposition, photolithography, and etching. So in deposition process, micro-thin film is deposited on wafer. So in this step, various materials are used. So for example, metal, insulated, or ceramics. So next, resist mask are patterned on deposited film by photolithography. So in etching processes, removing non-masked area using plasma or chemical agent. So repeating these processes, various devices are fabricated. I explain about our development approach. So as conventional approach, QFD activity target to expand the market by analyzing VOC and by improving the quality of a product. So this is just adapt to VOC approach. On the other hand, Fukuhara method QFD is creating VOC approach. So this approach targets to explore new market that welcome our technology by creating VOC. So we have explored the market welcoming our MEMS technology with Fukuhara method QFD. So in this activity, we concluded that it's need to reduce the particles on wafer. So on MEMS devices, particles on the wafer causes low reliability and low yield. So if those particles are reduced, we can improve market quality and mass production quality. So generally, particles on wafer are controlled at a mass production phase. But we suppose that particles were occurring in fabrication process and try to reduce particles at R&D phase. So this is just the front-loading approach. All the above, our objective of this research is 2 points. So one is achievement of objective function. So another one is particle reduction. So then I would like to explain about the definition of objective function. Okay, so this is a P diagram of the target system. So we take the etching depth as the output and input is the etching time. So noise factor is position on a wafer, process condition, and so on. So please see a lower figure. So this is a schematic view of etching process. The workpiece consists of 3 layers, so substrate, material B, and material A. In this process, we fabricate the device pattern on the material A. So during etching process, material A is removed by plasma. So etching depth output of this system Y is here. Material B is deposited under material A, so material B is not etched. However, at last step of etching process, material B appears on the surface and etched a bit. So we introduced operation window concept. So output is 2 etching depths and YA and YB. YA is etching depth for material A and YB is etching depth for material B. So in this case, our workpiece is material A. So our objective is to maximize the sensitivity for material A while minimizing sensitivity for material B. Then I talk about experiment and result. So in this page, we explain our experiment. So to better understand the etching process, we performed L18 orthogonal experiment. So we assigned 8 recipe parameters to L18 orthogonal array and in plane position on a wafer as a noise factor to outer array. So this is experiment result. This chart shows SN ratio of operation window. The result indicated that factor F has a significant main effect on the etching process. So factor F is related with etching gas. So this finding suggests that the reaction mechanism between material A and material B is different. So we performed robustness improvement respectively for material A and B. Next, this is the number of particles for material A and material B after the etching process. So as you can see, both results have a mountain and valley tendency. So this is suggests that reaction between control factors or external noises is very large. So the important point here is that comparing the number of particles, So as you can see, there's significantly different between the material A and material B. So significant different. Then I talk about discussion. Here, we discussed these results of our experiment. So the result of operation window SN ratio shows the etching reaction mechanism is a difference. On the other hand, the number of particles also significantly different. So for these results, we suppose that the difference of number of particles is caused by etching mechanism difference. So to investigate this hypothesis, we analyzed with reverse RFTA. So here, the target characteristics on the counterpart to objective of this research, operation window SN ratio and particle decreasing. So based on RFTA analysis, we focused seeds of particles. So discussing how seeds of particles occurs, we identified a new reaction mechanism, reaction 3, and devised a new control factor, factor I. So here, further discussion of devised control factor I. So this factor is etching recipe parameter, amount of the etching gas. So during this etching process, we used gas P. I mentioned before the material B is appears and it's bit etched at the end of process. So then gas P and material B happens chemical reaction, reaction 2. As a result of this reaction, the seeds of particles occurs. So when we introduce a new control factor I, so the etching process is proceeded with gas P and Q. So gas Q and material B will react as reaction 3. So this reaction has an effect of particle decreasing. So through this mechanism, we may decrease the particle by introducing a new factor I. Okay, through RFTA analysis, so we find the new, we may decrease the particle by introducing a new factor I. On the other hand, factor I has also the effect to operation window SN ratio. So it's expected SN ratio to be worse by factor I. To evaluate this effect, we performed a L8 orthogonal experiment. So this is the L8 orthogonal array we used in the evaluate experiment. We assigned factor I and B and C as a control factor. So the lines displayed as E1 and E2 are empty line. So these lines are used for evaluation for interaction. Okay, so this is the result of our evaluation experiment. Look at the left chart. So this shows number of particles. So as you can see, it demonstrated that the factor I has effect to reduce particle occurrence. So also, the main effect of E1 and E2 is very small. So this means interaction between these control factors are so small. And the chart on right side shows operation window SN ratio. We find factor C and I has a main effect to both of number of particles and operation window SN ratio. So in other words, factor C and I shows a trade-off. So in this research, we give prior to particle decreasing. So for operation SN ratio, we improve by other control factors with device construction. Okay, so this is the conclusion of my presentation. So we have explored the market that welcome our MEMS technology utilizing Fukuhara method QFD. So we reported the technology development approach to achieve the target characteristics and to reduce the particle occurrence during MEMS process on R&D phase. We performed L18 orthogonal array experiment to reveal characterization during etching process and revealed the difference of etching mechanism, difference the materials. And analyzing this mechanism with RFTA, we devised a new control factor. So to evaluate the factor of this new factor, we performed L8 orthogonal array experiment. And the effect of particle decreasing by this factor is demonstrated. So that brings me the end of my presentation. Thank you for your kind attention. Thank you.